Okay. Let's again first recap what we have learned yesterday and perhaps the day before yesterday. So the most important things we learned was first that the real part of the oscillation frequency of the superdense cloud is approximately equal to mu plus some alpha squared corrections. We have found an expression for the imaginary part of the frequencies, which ultimately dictates how quickly the cloud grows or decays, depending on where you are in the primary space. And this we found to be an expression that looks like this. Where this B, M, N, and L depends on alpha and A in general and just contains this whole expression that I don't want to write down again. Okay? So yesterday in the tutorial, I was told there was a question about why the inverse of omega I is called the E-folding time. So this is called the E-folding time. And so the reason for that is the following. The exponential growth of the scalar field is controlled by the imaginary part of the frequency. And so this is basically just t over tau I. Okay, so at t equals 0, e to the t over tau I is just 1. And then at t equals exactly tau I, then e to the t over tau I is equal to e to the 1. And then at t equals 2 tau I, this is equal to e to the 2, and so on and so forth. And so basically, each time t reaches 1 tau I, the amplitude grew by 1 power of e. And so that's why you call tau I the E-folding time, the time over which the amplitude grew by literally e, like 2.7 whatever. Okay? Okay, another important thing we learned was that the energy flux of the scalar field across the horizon is proportional to this combination. And similarly, the angular momentum flux of the scalar field is proportional to this combination. Okay? And so basically what this means is that whenever the real part of the frequency satisfies the superradiance condition, which is this condition, then the scalar field extracts energy and angular momentum from the black hole. Okay? So at this point, all of this we got from linear theory. What I mean by linear theory is literally the linear order in the Perturbative expansion around the Kerr background that we chose to study, okay? But here, because it's linear, it doesn't tell us what's going to happen once the amplitude grew through many, many E-folds and acquires, some macroscopic amount of the energy that is contained in the black hole. And to understand that, we try to model this growth and therefore the extraction of energy from the black hole in such a way that this black hole goes through a sequence of stationary Kerr black holes with successively decreasing mass and spin. Okay? So basically, nonlinear effects we modeled by a sequence of Kerr black holes. And the way we did this was to just assume basically that the mass of the black hole is now a function of time, okay? And the angular momentum equally is now a function of time, okay? And, you know, as the cloud extracts energy from the black hole, the mass and the spin of the black hole reduces in time. And so there were a couple of questions about exactly how this worked. So I just want to perhaps describe this in a slightly different way. So the way you can imagine this happens is the following. So let's plot the dimensionless spin chi from, you know, let's say 0 to 1. And on the x-axis, let's plot the mass of the black hole. And then let's assume that we start with some black hole that sits up here. Okay, so it just, you know, has a very large spin and some particular mass that I'm going to call the initial mass. Okay, and then the initial spin. And let's further assume that the black hole that we chose, or that the scalar field that exists around the black hole satisfies the superavariance condition. So the frequency omega r is smaller than m times the horizon frequency of this black hole. Okay? So just as a reminder, the horizon frequency is there's 2m a over 2m r plus, or equivalently j over 2m squared m plus root m squared minus a squared, or better, j over m squared. Okay? So basically, you should view omega h as not some number, but instead as a function of the mass and the angular momentum of the black hole. Okay? And so now we know that, okay, the mass and the angular momentum will change as the superavariance cloud grows. And basically what this will look like in this plot is something like this. Okay, so we start out with some black hole of some spin and some mass with some scalar field configuration around it that is super radially unstable, so it grows exponentially. And then through this exponential process in the energy extraction, the black hole loses both spin as well as mass to the superavariance cloud. Okay, and then it ends up down here at some endpoint. Okay, and so here I should say that, you know, the imaginary part is positive, so the scalar field grows exponentially. And so down here, the reason it stops here is basically because at this point, the imaginary part goes to 0. Okay? So basically, when the imaginary part goes to 0, the scalar field stops extracting energy and angular momentum from the black hole, and obviously then the black hole will just remain at that mass and spin. And where this happens is precisely where this part of the expression for omega I goes to 0. Okay? And because omega h is a function of m and j, where m and j can change over time, the omega h up here, so as a function of initial mass and initial angular momentum, this one is different from the angular frequency omega h of the final black hole because the mass and spin changed. Okay? So omega h of m final and j final at this point is exactly equal to omega r over m. Okay? So basically, as the black hole loses angular momentum, it spins down, and that implies that the angular frequency of the black hole reduces down to match the value of the frequency of the superintense cloud. And at that point, the growth stops. Okay, and then basically, using this expression, we were then able to actually find what this, how much angular momentum and how much spin and how much mass the black hole lost. So the mass in the cloud, which is basically just the mass that the black hole lost, we found to be the initial dimensionless spin chi alpha times the initial mass over m plus alpha squared corrections. Okay? And again, this we just got from this equation here. And then similarly, the change in the angular momentum of the black hole, or the spin of the black hole, we found also using this. And here I'm going to write it as the delta chi is equal to the initial dimensionless spin minus 4 alpha over m. Again, plus alpha squared corrections. Okay? But then, of course, this is only valid, these expressions for the cloud mass mc and for the change in the spin is only valid in the small alpha limit, because that's where we expanded the solution that we found through this formula, which is expand that's in small alpha to kind of simplify the expression. But in general, this is a bit more complicated. And so just to reiterate what we learned yesterday about this is that basically, if you assume that the spin is basically extremal, and you plot everything as a function of alpha from 0 to 1/2. At 1/2, again, the m equals 1 mode saturates. So let's focus on m equals L equals 1, as well as the overtone equals 0, because that's the fastest growing mode, as we found out. Then if you consider the full expression instead of just the expansion in small alpha, then the final mass of the black hole divided by the initial mass of the black hole looks something like this across the entire parameter space in alpha. Okay? And so basically the expression that we found here is just valid in the small alpha regime. And then one result that we found that was very interesting is that even at the maximum point, so where in the alpha regime in which the superintense cloud can extract the most energy from the black hole, at most, it can extract up to roughly 10% of the mass of the black hole. Okay? And then similarly, we can also plot the final dimensionless spin in this plot. So this looked something like this. So this is chi final. And again, in the small alpha regime, we already found the expression, which is what I wrote down here. But then if we, just plot the full formula, then it just looks something like this. Okay? And so basically what this means is that, okay, let's fix the mass of the boson, mu, and let's consider a black hole that has a particular mass such that m times mu is 1/4, right? Let's just pick a value. Okay, so then we sit right in the middle here. And so the superintense cloud or the scalar field of this mass around a black hole of this mass such that the alpha is exactly 0.25. This instability, or the instability of the m equals L equals 1 mode, will lead to a superintense cloud that has pretty much exactly 10% of the mass of the black hole once the growth stops. Okay? And so if the black hole mass was slightly smaller, then we would sit slightly over here in this plot, and so the mass we could extract is slightly smaller, okay? Conversely, if we are a bit further here, again, it's not as big, okay? But this all just depends on what the black hole mass actually is. Are there any questions about this? That's right, yeah. That's right, yeah. And this is, of course, only true for a black hole that has basically maximal spin. And if we picked a black hole that had lower spin, so let's say, let me draw I'm just making this up, I don't know the numbers exactly, but let's just say this is chi, 0.95, let's say, okay? Then, of course, it stops earlier because the saturation condition is at smaller alpha, okay? I don't know the value, but it's some value. But overall, these lines qualitatively look the same, but the numbers will just change slightly. Okay. Okay, and then one other question that I've gotten a lot is how to exactly do the perturbative expansion of the metric perturbations. So this was the idea that, the metric is basically some background metric, which we pick to be Kerr, plus some linear perturbation, plus order epsilon squared corrections. Okay? And then the question was, okay, how do we get this equation that I wrote down actually from the Einstein equations? How do we get this equation plus these gauge conditions? Okay? And I don't want to derive this here because it's extremely lengthy, but I can refer to this excellent review by Flanagan and Scott Hughes. From 2005, I believe, with the archive number 0501 041. And then specifically, this derivation is done for an arbitrary background metric in section 5, or specifically for a flat, so Minkowski background in section 2. Okay, so they are laying out all the details, but you'll see it's a lot of algebra, and I don't think you learn a lot by going through all the algebra. So that's why I'm not doing this explicitly here. Okay. Okay, so where we left off yesterday is basically expanding this to second order. And we learned that we had to go to second order because the stress energy tensor that is sourced by the superradiance fields, so that phi sub sup be the superradiance solution that we found at leading order. We found that the stress energy tensor is the square of this. And so basically this is order epsilon squared. And so therefore we have to go to order epsilon squared in this particular expansion. I should mention, yeah, never mind, it's the same. Yeah. Okay. And so basically doing this in the fashion that we wrote down yesterday, so basically you expand again to second order. Then we neglected the leading metric perturbations, again, because these are just decaying modes. And then we wrote down, at least schematically, the following equation. Okay, where here D is a second order differential operator. And so the question now is to understand, okay, what is the gravitational radiation that is sourced by the presence of this superdense cloud here? We basically need to solve this set of, I guess in general, 10 second order PDEs, okay? So this is again a very, a priori a very difficult and complicated task. But there is a formalism in place through which we can do this very easily. And in the following, I'm trying to outline this formalism, but I won't be able to derive all the expressions because it's just very lengthy. And so I'm just going to give you kind of the most important bits that you need to understand the formalism. And if you're more interested, you can go into the papers I'm going to list and see for yourself. Okay, so to tackle this, we're going to basically follow Tucholsky's approach. So basically, he studied perturbations of scalar fields, Maxwell fields, so just E and M, and gravitational perturbations on a Kerr background. And this was published in 1973. And ultimately, that's exactly what we're going to do. We're going to use exactly his approach, which basically simplifies this equation down to a set of two second order ODEs, similar to what we did when we solved for the scalar field itself. But some of the details are going to be slightly different. And so let me point out what the differences are. And so to point out what the differences are, let's introduce the aspects of the Newman-Penrose formalism. And basically the only aspect of this that I'm actually going to introduce, because it would definitely be way too much, is the underlying idea of the Newman-Penrose formalism is not to look at G mu nu, so the metric itself, but instead project the metric onto a quote-unquote null tetrad. So a tetrad is basically just four vectors at any point that are all orthogonal in a particular way that basically give you a frame at any given point, okay? So the only addition here is a null, and null just means that these vectors, instead of being time-like or space-like, what you might be used to for like a typical observer, they're now all null vectors, okay? And so the way to construct them is the following. So we define a vector L mu and a vector N mu. And the way we define them is basically, let me actually draw this somewhere else. So the idea is that one of them is the null vector that points radially inwards, and the other one is a null vector that points radially outwards. Okay, so we have time t, radius r, and so then we define L to be outwards pointing, I think. Yes. So L is outwards pointing, and N is inward pointing. Okay? So basically the square of each individually is just 0. But then to complete this, we would then have to come up with somehow a null vector in the other directions. But instead, what we're going to do is we're going to introduce a complex vector mu, which is basically, at least asymptotically, the following. So here, I'm going to assume R. Okay. And so basically, it's just a linear combination, a complex linear combination of the vector theta mu, which points in the theta direction, and then the vector phi mu, which points in the phi direction. Okay. So far, it's just a bunch of definitions. And then I'm going to define another thing, and this is called a Newman-Penrose scalar. So I'm going to define psi subscript 4. And this is basically just equal to some contraction of the wild tensor, okay? So the particular contraction it is the following, nu alpha beta. Where this overbar just denotes complex conjugation. So this is sometimes called the Weil scalar or Weil-Newman-Penrose scalar. Okay, so why is this particular contraction so interesting to us? And so the reason for that is because this contraction, this psi 4, contains the gravitational radiation at normal infinity. And to roughly see why that is the case, gravitational waves, we can do the following. So basically, psi 4, which is some complex scalar, is, depending on conventions, the second time derivative of the plus polarization plus I times the second time derivative of the cross polarization. Okay? And one simple way or one roughly simple way to see this from this expression is the following. So in spherical coordinates, you can write these polarizations in the following way. And then okay, so this is basically just writing the polarization states in spherical coordinates at large distances. Okay, and if you go through this derivation here, you'll see that the perturbation, so basically the linear order Riemann tensor that emerges from this H, or equivalently the leading order Weil tensor at large distances, where it's basically vacuum, and so the two are the same. There, this is so these expanded in terms of what is written in terms of Riemann tensors is R T theta T theta plus I R theta R phi. Okay. I'm dropping some terms, so it's basically a sum over several of these terms, but roughly speaking, those are the contractions that are that basically give you these components, and these components in turn are then the polarization states. And then, of course, you can see that comparing this and this, it already looks very similar. Okay. And in fact, if we then, kind of glance at the way we defined M and the way we defined L and N, so L is basically, again, yeah, L is basically T mu plus R mu. Yes. And N is minus R mu. Okay? So the T and the R and the theta and the phi, if they are contracted with the Weil tensor or equivalently the Riemann tensor at large distances, then you just get exactly the components with respect to those coordinates. Okay? So you can kind of intuitively see now, not exactly, but you can intuitively see why this is equivalent to this at large distances. And then in turn, this is this, and therefore the polarization states. So ultimately, this complex scalar psi4 contains the two polarization states of the gravitational waves that are emitted from some system at large distances. You mean here? No, not really. So I think the sign here depends on the convention you choose, actually. But ultimately, you can also see that the sign doesn't really matter because the plus and the cross polarizations are basically sine waves. And so the sign will just give you a phase offset in the sine waves. Okay. Okay. So basically what we need to do is somehow compute this psi4 that is sourced by the presence of the superimmense cloud. Okay? So somehow we need to convert this equation for the perturbations of the metric into an equation for psi4. And this is exactly what Tucholsky did back in the 70s. And basically how the way he did this, and we're just going to say this in words, is he used this Newman-Penrose formalism in which you basically expand all the relevant quantities. That is, you define these Newman-Penrose scalars, which contain basically the degrees of freedom that you're after, so basically some contraction of the Riemann tensor. And instead of just defining the psi4, you might already guess the 4 indicates that there is a 0, 1, 2, and 3. And that's exactly the case. So basically what you do is you define 5 of these scalars, and each scalar is a complex scalar. And so there's 2 degrees of freedom per scalar. So you have 10 degrees of freedom, which is exactly the same amount of degrees of freedom you have in the metric. Okay? So basically, it's just rewriting the degrees of freedom in a slightly different form. Okay? But then it turns out that for the Kerr spacetime, some of these scalars are 0. In fact, all of them except for a single one is 0. And the reason that it is 0 is just because Kerr is special in many, many different ways. And one way in which it is special is that most of these scalars are 0. Okay? And so then the kind of idea is, okay, how do we get perturbations of these scalars? And so this is basically, I'm just going to write this schematically. You're going to, again, similar to the metric perturbations that we expanded around some background, you can then expand these scalars also around some background. Okay, so you can write this as psi4 Kerr plus epsilon squared psi for perturbation. Okay? And you can do this for all these scalars, and then you can take advantage of the fact that the psi4 for Kerr, for instance, is 0, and then many of the others are also 0. And because they are 0, all of these equations simplify significantly. Okay? So really the crucial point of using this Newman-Penrose formalism is to make use of the fact that most of these scalars are 0, and therefore the equations simplify substantially. Okay? Yes, this is epsilon squared. In the original work, they're considering quote-unquote linear perturbations. The terminology doesn't exactly line up with the terminology I've been using, but basically the equations are identical. I'm simply considering the second order because we also have some source, and Tucholsky wasn't really after trying to understand sourced perturbations, but instead of just freely decaying perturbations that don't have a source. So the terminology is slightly different, but the equations are identical. Okay. And so then basically the remarkable fact that Tucholsky discovered was that you can actually write down a very simple equation for the perturbation of psi4 that separates into two second-order ODEs. So let me just draw this. And so I'm just going to write down the solution to all the derivations that he went through. So ultimately, the equation that we're going to get is the following. So we assume that psi4, I'm going to call it psi4, not psi4 perturbation, because basically the Kerr value is 0, and so there's no ambiguity in defining what psi4 is. So psi4 is just the one component or some components of metric perturbations sourced by the two-Brownian cloud. Okay? So we can expand this psi4 in the following way. So rho times lowercase psi, where lowercase psi is kind of what we had already looked at. Okay, so the ansatz for this lowercase psi is the same as for the scalar field. And then you get psi4 by multiplying it by this rho to the 4. And this rho to the 4 is just, or the rho is just r minus I a cosine theta. Okay? So for now, I just kind of, rewrote this psi4 in a slightly different way, and then assumed that it looks something like this. And if it does so, then basically the equivalent equation to this equation for psi4 separates into a polar equation, which is the following. Okay. So here I defined A. So A is basically the separation constant. Again, this approach is extremely, or basically identical to what we did for the scalar field. And so A is just a separation constant, which we define to be minus. So basically, we just rewrite A in terms of a different separation constant, lambda, in this particular way. Okay? And then the radial equation, and I'm going to explain exactly what any of these terms mean in just a second. here I defined K, or rather Tucholsky defined K to be this expression. Okay. So one thing that I haven't defined yet is what this lowercase s is over here. So we have an uppercase s, which is just from our ansatz. But then we have a lowercase s as well. And this lowercase s is called the spin weight, or I'm going to call it the spin weight now, because for all our purposes, this is what it is, spin weight. And so basically, s equal to 0, you have seen the equation for s equal to 0 already, okay? So for s equal to 0, this term disappears, this term disappears, this term disappears, the s is 0, and a just turns into some function of lambda. And this equation is exactly what we found for the scalar field as well, except that there was a mass term on the right-hand side, okay? So basically, for s equal to 0, this gives you the perturbation equation of a massless scalar field on a Kerr background. Okay? So s equal to 0, massless scalar perturbations on Kerr. Okay? And so kind of the magic of these are called the Tucholsky equations. Maybe I should write it over. Tucholsky equations. I hope this is still visible online. So these two are called the Tucholsky equations. And the magic here is that if you plug in s equal to 1, then you basically get the perturbations of an electromagnetic field around a Kerr black hole. So that is a different set of equations that govern certain degrees of freedom of the electromagnetic field, or of linear perturbations of the electromagnetic field around a Kerr black hole. Okay? And then similarly, so let me write this down. So basically, EM perturbations on Kerr. And then similarly, for s equals to 2, you get tensor perturbations or metric perturbations on the Kerr background. Okay? And so it's really remarkable that in with two equations, you can understand the perturbations of master scalar fields, E&M fields, and metric perturbations on the Kerr background. Okay? So we, and by we I mean Tucholsky, was able to reduce these 10 second-order PDEs that we would have in principle to solve for just the metric perturbations. He was able to reduce this to 2 second-order ODEs, which also happen to govern the dynamics not just of the metric perturbations, but also of scalar perturbations, E&M waves, and so on. Okay. And right, so the 0 here is basically mostly what Tucholsky considered. But of course, 0 corresponds to no source. Okay? But of course, we have a source. And so this is not actually 0. This is some function g of r, where g is then some particular Newman-Penrose expression of the stress energy tensor that is given by the superintense cloud. Okay? So basically, the g will contain terms like, I'm just going to write this in quotation marks so you can get a feel for how the g is constructed. This will contain some contraction of this with n and m, and all the other null vectors. Okay? And so that way we can construct this g. Yes, that's right. So basically, because the equations are the same for the linear perturbations Stokowski considered and the quote-unquote quadratic perturbations that we are considering, the only difference really is accounting in epsilon. And ultimately, this difference will only result in this G being 0 or non-zero. So if it's 0, then it's basically linear perturbations on the Kerr background. If it's non-zero, and the source is given by the square of the scalar field here, and we adopt this counting where the scalar field by itself is linear perturbation, then this is basically the equation for the second order perturbations sourced by the fields. Okay. Yeah, the terminology is somewhat confusing here, but I think it's important to emphasize that it's actually a second order effect. So at linear order, we can just solve the Klein-Gordon equation without worrying about any of the metric perturbations. And at second order, we can only solve, or we only need to solve this equation, and we don't need to care about what the Klein-Gordon equation does. Okay. And so now the new goal, I guess, is to solve these equations. First the polar equation and then the radial equation. And we're solving this for s equal to -2. So for lowercase s equal to -2, this corresponds to the psi 4 that we want. There's a particular reason why it's -2 and not +2, but that's just a technical detail, okay? Okay, and so let's first look at the polar equation. So we had already seen that for s equal to 0, and basically the spin to 0, this will just give you the spherical harmonics. But for s equal to -2 or s anything that's not 0, it can't be the spherical harmonic, but instead it's called the spin-weighted spherical harmonic. So for polar solution, for a omega to 0, the solution is usually written as -2, so for s equals to -2, Lm, and then theta phi. And these are called the spin-weighted spherical harmonics. Okay? But this is only the case for this combination a omega to 0. And so for a omega non-zero, it's basically you get a family of solutions for each a times omega. You get a slightly different solution. And the solution will always reduce to these spin-weighted spherical harmonics for 0 a omega. But for non-zero a omega, it will be some deformation away from that limit, okay? And I'm going to note them by S. And in general, they depend on this combination. And so these are called the spin-weighted spheroidal harmonics. Spheroidal harmonics. Okay? And basically, I don't want to write down an expression for this. In general, you can only find it numerically. In the small a omega limit, you can find some perturbative expressions, but ultimately, it's not too important what these actually are. One important fact about them, though, is that they form a complete basis. So basically, and perhaps I should not be sloppy with the dependencies. because technically it doesn't depend on phi, but usually people include that dependence. So it's basically just the e to the I m phi that they add, that they include in the definition of this or not include in the definition. But basically, these form a complete basis, and so you can expand any function of theta basically in these spheroidal harmonics. And so that's exactly what we're going to do with our psi4. Okay, so we already know that the psi4 is basically of this form. Okay, where S is now a spin-weighted spheroidal harmonic. Why would we use the second one? Right. Right. So if we wanted to write this lowercase psi over there, in terms of, you know, sum L comma M of, let's say, -2 Lm, e to the minus plus I m phi. This is what you're imagining with some, you know, coefficients Lm that depend on R. This is kind of what you're imagining, right? So the question is why we would choose the S here, A omega, instead of the Y, correct? And so the reason for that is basically because if we did this with Y, the Y is not a solution to this, right? So then we would have to have a bunch of terms that all kind of, and basically infinitely many, because in general you would get infinitely many of those. And then you would have to sum up all of these different terms. Instead, if you just used this to expand this, then you could just get a single term, because it's already a solution to the polar equation. Okay. Okay, so right. So in general, we will then get the gravitational waves. Psi4 is equal to rho to the 4, which is from over there. And then it's basically R. I'm going to add some indices here now. Okay. So the only thing that really changed from over there is that we now know, okay, this S must be, or it is convenient to choose these spheroidal harmonics, which are a solution to the polar equation. Because otherwise we'd have to replace this S by a sum over, let's say, the spin-weighted spherical harmonics, so the spheroidal harmonics. Okay? And of course, in general, for us, the A times omega is going to be non-zero, because the A is the spin of the black hole, which is non-zero, and the omega is going to be the frequency of the perturbation. And because the source has a non-zero frequency, the perturbation will have a non-zero frequency too, and therefore the A times omega will be non-zero also for us. Okay, and so because we know that psi4 is basically exactly what we're after, so the plus and the cross polarizations, we can also get the total energy flux in gravitational waves that is basically sent out by, so far, just a generic source, is sent out to null infinity. And so the way to get this, and this is just going to be a formula that I'm going to quote. Again, this all follows from Tucholsky. okay? So basically what this means is that, okay, we have found a solution to the polar Tucholsky equation. And then we were able to write down psi4, which basically contains our gravitational waves that we're interested in terms of these spheroidal harmonics. But there's still this dependence on R, okay? But once we find this and we can construct the psi4, we then know both the total gravitational wave energy flux at infinity, and we also know the polarization states H plus and H cross, which basically contain all the information that we would want to know about the gravitational waves sent out by the superhens cloud. Okay? So the only thing that's left to do, quote unquote, only thing that's left to do is solve the accompanying radial equation. Okay, so similar to what we did for the scalar field and this hydrogen atom solution, we found a solution to the polar equation very quickly. Here I basically just wrote down the solution and defined it to be a solution, but you can construct this explicitly. But ultimately the work you have to put in, you really have to put in to solve the radial equation, not so much the polar equation. Okay? So let's focus on the radial equation. Okay. Okay. And so the way to do this, so again, recall the radial equation is this second order ODE with some source GR, where this G of R basically is somehow constructed from the stress energy source by the super-Arians field. Okay. And so the way we're going to solve this equation is using a Green's function. And because ultimately we are interested in a particular solution that is, particular to the source that we are imposing. Okay? Okay. So the way I want to proceed is not to derive the Green's function, because again, that would just take too much time. But I'm gonna give you a flavor of where this Green's function might come from without actually deriving it explicitly. And I'm gonna assume that you guys have heard of the Sturm-Liouville problem. Yes, no? No, okay. Okay, well, then this is gonna be even more new to you, I guess. Okay, so perhaps I should explain in general then what a Green's function does. Do people know what a Green's function is? Okay. So then I don't need to explain what a Green's function is. But basically, ultimately, let's say we have some second order operator L that acts on some function with a source f, which is exactly what we have over there. Then basically the inhomogeneous or the particular solution, is basically some integral, let me call it dx prime, over the Green's function the convolution of the Green's function with the source f. Okay? And the way we're going to solve our radial equation is exactly using this. Okay? Yes. We could, yes. But in general, it will still be very difficult to solve. And also, with this Green's function, as you'll see, actually solving the ODE will reduce to taking a single integral. And so it's just simply more convenient to use the Green's function instead of doing what we did for the scalar field, basically. Because ultimately we're only interested in the psi4, so the gravitational radiation, at large distances. Okay, so for the scalar, we were interested in the scalar field everywhere in the domain, not just at infinity. But here we only care about the gravitational waves at infinity because that's where we detect the gravitational waves. Okay, so that step again will simplify things even further. Okay, so let me tell you how this comes about. Okay. Okay, so then let me motivate the way to construct this Green's function. I'm not going to do it exactly for the problem that we have, but I'm going to do it for, we're going to write down the solution for this Sturm-Liouville problem. And yeah, if you're interested in, you can just Google Sturm-Liouville and you'll find something immediately. So what is this? It's basically a particular second order ODE that has some general form and some general differential operator L. And that assumes you have certain boundary conditions at some distances. Okay, so basically it's just a, some ODE with boundary conditions, or some sourced ODE with boundary conditions. And within this framework, you can write down an expression for the Green's function basically immediately. So you don't need to solve something like, LG of x equal to delta x minus x prime, which is, in general what we'd have to do. And then somehow construct the Green's functions by reversing this. But there's a general procedure to do this in this framework for a particular subset of ODEs, okay? And the ODE that we're interested in is not exactly of this form for some technical reasons, but basically the Green's function is going to be, look basically identical, okay? So, yes. So let me just write down what the Green's functions in general will look like. Okay, so basically, the assumption is that you have a setup like this on an interval that goes from A to B, okay? And then you can construct a U and a V where the U satisfies the boundary conditions at x equal to A, and then V at x equal to B. Okay? And then this P here, now I was kind of assuming that you had seen this before, but this P is basically appears in this operator L. Yeah. In general, this is called, or sometimes this is called the Vronsky. Okay, so I didn't realize this was all news to you, but yeah, basically, if you Google this, you'll find plenty of explanations where this comes from. But basically, the construction to get here is basically exactly starting at this definition for just the Green's function. Okay. Okay, and so that's exactly what we're going to do, just that the expression is going to look slightly different for us. So let's go to the radial-Tokowski equation. And basically import this formalism, although I should stress there are some technical differences about boundary conditions, but the form of this is at least the same. And if you're interested in the details of how this Green's function is constructed, in the case of the radial-Tokowski equation, then you can look at so the details are in now this is an old paper, but I think it's actually quite easy to read on resonances. I don't know, resonance oscillations. So oscillations of rapidly rotating black holes. Okay. Okay. So ultimately, what is our solution going to look like? Now we're looking for a solution for R, so the U is just going to be R. And then we're going to integrate over some R prime instead of X prime. And then we have the Green's function. So the Green's function is basically a homogeneous solution that satisfies the boundary condition on one side times the homogeneous solution that satisfies the boundary condition on the other side of the domain. And then that's multiplied by the source term. Okay? And so we need to do the integral over all of X prime. So we need to basically have an integral that goes from basically minus infinity to, or from A to X, and then from X to B. Okay? Let me write this out explicitly. So basically the solution R Lm omega of R is, how am I going to write this? So the Vronskian, again, this is similar to what we had here. This C is also the Vronskian, and it's exactly the same form. I'm going to write it out in a second. And then we have R out, which is basically a homogeneous solution to the Tokowski equation, the radial-Tokowski equation, satisfying the boundary condition at one of the ends. And you know what? Let me just write it out first and then explain it. I think that's better. Okay, so where R out at large distances goes like I omega R, and R in goes like e to the minus I omega R, R star technically, for R to R plus. Okay? And so these are homogeneous solutions to the radial-Tarkovsky equation. Okay. And then the Wronskian is equal to 1 over delta, and then R out derivative R in minus R in derivative R out. Okay. So comparing the Wronskian, we can already see that's basically exactly what we had over here, right? It's just one of the homogeneous solutions times the derivative of the other minus the second homogeneous solution times the derivative of the other, okay? That's exactly what's happening here. Then we have our two homogeneous solutions, basically, which satisfy the correct boundary conditions on one end of the domain, which is R to infinity in our case, and then on the other end of the domain, which is the horizon at R plus. And so, of course, at the horizon, we're imposing ingoing boundary conditions. So any perturbation that crosses the horizon should only go into the horizon, not come out. And at large distances, we have outgoing boundary conditions, because now we're dealing with gravitational waves. And so we're assuming there's no gravitational waves coming in at infinity, so it's only just source and going out. Okay? And so then the inhomogeneous solution, so the particular solution to our sourced radial Tarkovsky equation, is just this convolution of a Green's function times the source. And the Green's function has this particular form, where you have this product of the two homogeneous solutions. And that's exactly what we have over here, right? So we have this integral over dx prime, which is basically just split into two regimes, one where x is larger than x prime, one where x is smaller than x prime, which in our case is just r prime is smaller than r, so between r plus and r, or r prime is between r and infinity, okay? So we're just splitting up the integral of into two integrals to rewrite this expression in a single line, okay? And then you can also see, basically, in the integrand is basically just a product of one of the homogeneous solutions, multiplied by the source gr, which is exactly what we have on the right-hand side over here, okay? And then I pulled out one of the other homogeneous solutions just out of the integral, because it just depends on r, similar to here, where one of them depends on x prime, the other one only on x. Okay? And then convert the same is true for the second term as well, just flipping the homogeneous solution. Okay. So I realize that this is all a bit new to you, but I hope the general idea is clear, that we are constructing a Green's function using some machinery through which we can construct it. And then we're just applying it to the problem that we're trying to solve, where we then get this expression for the solution we're interested in. Okay? Is this general approach here? Well, I mean, the easy answer would be that's what pops out of the math, but I guess that's a not very satisfying answer. Yeah, let me think about it, and I might get back to you. But yeah, ultimately it pops out of the math, which is kind of the easy answer. Yeah, let me get back to you. Any other questions? Okay. Okay, so now we have a general procedure to get our solution that we're interested in. Okay? And so we can simplify this still a little further. And the reason for that is because, as I was saying before, we're not interested in the solution for all R. We're really only interested in the solution at large distances because we only care about psi 4 and therefore the gravitational waves at large distances. Okay? So the solution then basically one of these terms, this term will just be 0, and you're just left with the first term. Okay? And yeah, so let me just write this out. Actually, I forgot the square here. Okay. So basically, this can be simplified further by basically plugging in the boundary conditions that are in satisfies basically the solution of the equations expanded around R plus. What the solution will look like at large distances. So if you plug this in, then you write out the Vronsky, which is basically just depends on the two homogeneous solutions, which we haven't found yet, but we'll find them in a second. Then we will get the answer, which is okay. So what happened here is basically I simplified the Rn as well as the Vronskian by just plugging in the homogeneous solutions. And then noting that the homogeneous solution that satisfies the ingoing boundary conditions on the horizon at large distances basically has this particular form. Okay? And then I introduced this B in, where the B in basically just is a normalization. Okay? Because you have this R in here, and the homogeneous solution, you only know up to normalization. And so you still need to normalize the homogeneous solution correctly. So that's why there's this normalization factor. Ah, yes. 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 Okay, then it makes more sense. Yeah. Yeah. Okay. Right. Okay. Okay. So basically, now what we were able to do by using all this machinery is to get the information that we want from the solution of the Rayleigh-Tarkovsky equation by just performing, quote unquote, just performing an integral over a homogeneous solution to the Rayleigh-Tarkovsky equation, convoluted with the source term g of r, and then, yeah, weighted by this delta. Okay? And so the question then is, okay, what is this homogeneous solution? And basically, people have computed the homogeneous solution. It's an entire separate process, but basically, one set of homogeneous solutions you can use are basically the ones that were found by these authors. In 1996. And usually, these solutions are just called the MST solutions, taking the initials of the authors. Okay? So basically, there is a way to construct these homogeneous solutions that we don't really care about too much. Basically, they just give you an expression for these solutions. And then with this expression, you can then perform this integral once you have constructed the G, which you can construct very easily just for the superintense cloud through some contraction with the stress energy density. Okay. So okay, so is this roughly at least a general idea clear to everyone? Right, so Rn is a homogeneous solution, and the in just refers to that it satisfies the ingoing boundary conditions at the horizon. Yeah, they found the homogeneous solution, which I called Rn. But the in just comes from the fact that it satisfies ingoing boundary conditions. Yeah, then the terminology is perhaps somewhat confusing. But both R in and R out are homogeneous solutions. Okay. Right, so this R in as a function of R at R plus will look something like this. So this is just the boundary condition. And given this boundary condition, they found the full solution for all R. The full homogeneous solution for all R. Yeah. Which you will need. You need for all R because you're integrating over, from R plus to infinity. So you need the whole range. Okay, so what can we learn from this? Okay, so what can we learn from this without doing this integral explicitly for now? Just kind of the most important bits that we can learn without doing the integral. So first of all, what we could already guess. So this goes like the square of the super n solution. And the super n solution goes as e to the I omega t. So this will go as e to the 2 I omega RT. Okay. So the frequency of the source will be 2 omega r, which then also implies that the frequency of the perturbation will be 2 omega r. Okay. So I'm going to denote this as omega GW, where this omega GW is just the omega that appears in this expression here. So this is 2 omega r. Okay. Similarly, for basically the exact same reason, the azimuthal dependence of the source looks something like this. So now we have a 2m phi instead of the 2 omega RT. And for the exact same reason, this means that the azimuthal index of the metric perturbation, mgw, is 2m. Okay, so where the lowercase m is the azimuthal index of our super n state, and then mgw is the azimuthal index of the metric perturbation. Okay? Okay. And then one last important fact that we can already see from this is the following. So we now have a solution. We now have the solution at large distances. And we know it's just a convolution of the source term, where the source term enters linearly. Okay, so this is g, not g squared or 1 over g or anything like that. Okay? And so what this means in turn is that our psi4 here goes linearly in the source term g. Okay? So let's write this down. Psi4 is some proportional to some integral g times r. Okay, so this is just kind of schematically writing this. Okay, the important fact is that it goes linearly in g. Okay, but g is some expression that goes linearly in the T mu nu, or some contraction of the stress energy tensor. Okay, and so basically what this means is because the stress energy tensor goes like the square of the solution, this will also go as some integral over the square of the solution. Okay, I'm just writing this out schematically to kind of collect the powers of the super n state. Okay. Similarly, we know that the mass of the super n's cloud is basically just an integral over the energy density of the super n's cloud. Okay. And the energy density in turn is just some component of the stress energy tensor. Okay, basically the 0, 0 component. Okay? And so this is basically just a volume integral over the superintendence cloud squared again. Okay? So what we learn from here is that the cloud mass goes like the square of the superintendence amplitude. Okay? And so combining this, we then know that psi 4 goes like the mass of the cloud. Okay? Just the overall normalization. Okay? But we also know that the energy flux of gravitational waves goes like the square of psi 4. This we wrote down over there. And so this goes like the mass of the cloud squared. Okay? And so basically what this implies is that the gravitational wave energy flux, so the energy emitted by the oscillation of the superintendence cloud, is some number or some function of, you know, the spin and the alpha, etc., but it's also proportional to the mass of the cloud squared. Okay? And the last thing I'm going to tell you today is, so this we can all get without even doing this integration. Okay? We just looked at, you know, basic scaling relations. We compared the powers of the superintendence cloud and then got these things. But to actually get not just the proportionality here, but to understand what the function is up front and the numerical value, we then actually need to do the integration. Okay? And the integration in general, you can only do numerically. But you can do some approximations, again, in this small alpha limit. I won't go through the steps of exactly how to do this, but there are some simplifications you can make to simplify this integral and do it analytically. Okay? So let me just give you the results. So for alpha much smaller than 1, and for the m equals L equals 1 and 0 overtone state, we get that the gravitational wave energy flux from the scalar cloud is equal to C, where C is some number that I'm going to give you in a second. Okay? And then we can do the exact same thing. All right, let me first write down the number. So C basically depends on what kind of approximation you make in this integral. And so basically there are two ways of approximating this, and both are kind of not quite right, but they kind of get the ballpark correct. So there's a C flat, which is 1.5 times 10 to the minus 3. And then there's a C Schwarzschild, which is 2.5 times 10 to the minus 2. Okay? So the reason they're called flat and Schwarzschild is basically how many terms you keep in this expansion. So basically, if you do this small alpha expansion, as we saw on Tuesday, the more terms you drop, the less relativistic effects are there, and the more you only care about large distances. Okay? And you can take that to the extreme where you just drop all terms. And you just do this on a flat spacetime, basically. So this delta will just turn into an r squared. And this Rn will just be the homogeneous solution to basically the equivalent in the flat space limit. Or instead of just going all the way to flat space, you can go to just Schwarzschild, which basically just contains the mass term. So that's kind of the leading order correction in alpha. In doing that, you get a slightly different number. But ultimately, both of these numbers are not quite right. The actual correct value is somewhere in between those two numbers. Okay? And then the last thing is one I want to quote is basically just the same for vector fields, which you'll need for the tutorial. So there we have D. Okay, so you can go through the exact same exercise just roughly outlined, instead of just for the scalar cloud, now also for a vector cloud. And the results you get kind of look qualitatively the same. It's just that the final expression looks slightly different, so you have a different numerical number, but you also have a different scaling in alpha. And what this different scaling will imply is that the total energy flux from a vector cloud is much, much larger than the energy flux from a scalar cloud, and therefore the gravitational wave amplitude is much larger. Okay. Are there any remaining questions?
Okay, so we're already a few minutes beyond the hour, so maybe we continue with the questions over lunch, and thank Nils for the lecture.